Yeah. Right. Cool. Hi, my name is Lev. I'm a grad student at the University of Maryland. I'm also at Never Local. They work on beyond QKD applications of QKD infrastructure and near-term quantum memory stuff. So you can find the paper on this archive. We'll get into what all these things mean, but yeah. So really, the high-level goal of this talk is we're going to be working towards a specific construction and proving its soundness. But along the way, we're going to learn a couple of things having to do with quantum and error correction. Specifically, we're first going to go over these things called quantum random access codes. Then we're going to talk about different models of adversaries in a constrained quantum setting, so where like quantum circuits are noisy. Then we're going to work towards our proof, take a step back to go over some information theoretic ideas, and then finally give the proof outline and the conclusion. So all this talk isn't quantum error correction, it is quantum plus error correction, which should be pretty close. Yeah. So first, like, what are we going to be working towards in this talk? So a one-time program is a cryptographic primitive introduced by Goldwasser and a few other people in 2008. And really, they're this like kind of non-physical primitive. Like I give you some state or some circuit or whatever, and you can use that to execute a function once, and then your ability to execute the function again self-destructs. So it's stronger than black box obfuscation because there you can evaluate multiple times. Here you can evaluate once. And it's like obviously impossible in the classical setting, right? I can not give you a string that's going to delete itself because you can just copy that string. It's also impossible in the quantum setting to do with like, if your program's deterministic, you can like undo your computation. You can't actually destroy information, but we're not getting too much into that. But just know that's impossible. But if you could build these things called one-time memories, then you could actually build one-time programs. So that's the primitive we're going to be working on in this talk. And what they are is they allow you to store two messages, M0 and M1. And they allow some user to read one of the messages. And then once you read one of the messages, the other one self-destructs. And for those of you more familiar with like MPC or garbled circuits, you can kind of think about this as like a non-interactive oblivious transfer, or you can like encrypt the wires to your garbled circuit, but not too important. Just this is what we're building, and it gives you one-time programs. Oh, by the way, stop with me with any questions throughout the talk. It's totally fine. So to get to our final construction and what we're going to be trying to do, we're going to introduce something called quantum random access codes, which were introduced by Binance et al. Like 25 years ago. And there's really cool primitive where, thankfully, Giuseppe introduced all the quantum stuff earlier, so we don't have to reintroduce that. We're going to take m messages, and then we're going to try to pack them into n qubits, where n is less, number of qubits is less than the number of messages. And then we're going to send them to Bob. So Alice has their messages, send them to Bob. And Bob can choose an index to retrieve any one of these m messages, apply some unitary corresponding to the index, and then try to measure that message. Bob's not going to succeed with 100% chance, but Bob can still, with some decent non-negligible probability, retrieve one of the messages. That's the high level. Yeah.
So are the messages just symbols or
yeah? They can. So in this case, just think about it as arbitrary strings of like a fixed size. So you can just think about this as bits. Like x1 is like either 0 or 1, x2 is a 0 or 1, but this is the general like.
But so that is the entire message, or you
Sorry. Yes. Yeah. They're separate messages. X1 through XM are different strings. Yeah. And the idea is that Bob can only recover one of the strings, or Bob can recover one of the strings with better probability than the other ones. Yeah. So it's like success. So there's one specific random access code that's the simplest one, the first one introduced, where we're going to encode 2 bits into 1 qubit. So we're going to have bit 0 and bit 1, and we're going to do this like calligraphic E is going to be our encoding function. And we don't have to worry about the mechanism too much, but for those interested, we can kind of represent a single qubit in a simplified way without any like imaginary numbers as being a point on this like circle. If we want to encode the message 0, 0, we're going to encode in the state that lies here. So it's going to be closer to the 0 state. It's like the pi over 8 state. And then 1, 0. And really the idea is if you imagine that you want to measure, let's say, the first bit, right? So let's say we encode message 0, 0, we measure the first bit. We're going to measure the z basis, which corresponds to 1 and 0. And the way we can calculate the probability is by projecting onto this basis right here. We're going to project here, and then the chance of measuring a 0 is 85%. So with 85% chance, we're going to measure out b0. And we can do the same thing for the other bit. If we want to measure the second bit, we're going to measure along this basis. And with 85% chance, we're going to measure our right bit. OK, so I think we also went over coding yesterday. And here we have a 15% chance of measuring the right thing or the wrong thing. Let's say we want to encode some larger message and have a user read out this larger message. We can use error correcting to remove the errors that we add in this measurement process, right? Again, every time we do a measurement on a single qubit, we introduce some chance of error, right? So if we choose a, oh yeah, yeah.
But
yeah.
How do you distinguish the 0, 0 from the 0, 1?
Yeah. So you distinguish, if you're going to measure the second bit, we're going to measure along the x-axis, the x basis, so this negative and plus, yeah. So you have to choose your basis to measure the, yeah. So what we're going to do is, remember we have these like, we can pack m messages into one random access code state. We're going to take m code words from an error correcting code that can correct up to the probability that we need to remove any errors introduced in the measurement process. And then we're going to encode it into a single qubit state. Yeah. So for example, we're going to take n of the, so our code words have length n. We're going to take n of these quantum random access code states, encode our m different messages into each one of these states pairwise. And then to retrieve our original message, cj, we're going to apply a unitary uj corresponding with one of the messages, and then measure. We're getting some errors on these measurements, and then we're going to correct. So we can recover one of these code words. And like, I guess you might be wondering, why is this useful or interesting? Well, I mean, it gives you like some bounds, but it's actually not that useful or interesting until you start introducing some further instruction ideas, which we're going to get to shortly. OK, so as before, here we do our measurement before we decode, but we can actually just do our measurement after decoding and make it sort of non-destructive. So we can actually recover both messages, C0 and C1. Right? So in some sense, we haven't done anything too interesting. I could have just sent Bob both messages C0 and C1 classically, and I didn't have to engage in this whole protocol. It doesn't really give us anything super cool. OK, but the question is then, what if we actually have a weaker adversary, right? Like these decoding circuits right here to get out C0 and C1 in a non-destructive way, they can be pretty expensive. And they have to be quantum circuits. And quantum circuits are expensive, and we don't really have them today. Not to mention, if we have these states being given over like quantum key distribution networks, they might be pretty noisy and hard to work with. So it's possible that we're not going to be able to do actual decoding in a quantum coherently setting, in a quantum coherent manner. So our construction idea is really to use this idea of sending a message with random access codes plus error correction. But if Bob, the adversary, tries to recover both C0 and C1, their decoding circuit, which is a quantum circuit, is going to be noisy. And because it's noisy, it's going to corrupt the output for C0 and C1. And we're going to want to show that Bob will not be able to recover C0 and C1. And if you guys remember, this gives us a one-time memory. If we can construct something where Bob will only get C0 or only can get C1, then we have a one-time memory. And if this whole thing is impossible, then we're good. So we just want to show that Bob can only recover C0 or C1, not both. So the idea for the one-time memory is we're going to take random access code that tags in two messages, so the example from before, and two code words, C0 and C1. And we're going to want to make sure that Bob can only recover one of them, C0 or C1. And the way that this is going to work is we're going to have all these states, these n states that Alice is going to give Bob, phi1 through phi n. And to recover the first code word, just measure the z basis. And then to recover in the second code word, we're going to measure the other basis. And then we decode after. So decoding is classical. And decoding is really the expensive part. This like quantum circuit right here is very cheap. It's very short. And that's going to be our high-level idea. Just as an aside, I don't want to get your guys' hopes up too much. This does use random linear codes, which take an exponential time to decode classically, which is a side effect of our proof. But if you guys have any ideas of how to get rid of that later, I'd be happy to hear it. Yeah. Before we move on, does anybody have any questions about where we've gone so far? Okay. Yeah. Yeah. Yeah, we're gonna get to that. Yeah. That's like the big like that, because really the question's like we have this construction, but this is not a proof. Like this is the opposite of proof, right? This is like, well, the adversary could do this, but maybe it's gonna be noisy. So really the question's like, how do you define your adversary, and then how do you prove that the adversary cannot recover C0 and C1? And we're gonna have to use random codes to get that proof. Yeah. Yes, yeah. The problems we actually need less structure. Like the less structure, like you'll, yeah. The structure's bad for our proof. Yeah. So, so we're gonna take a very specific model of quantum computation, and it's pretty restrictive. And the hope is to remove this restriction in the future. But we're gonna assume that we have a quantum circuit that we can apply to our input states. This quantum circuit is going to be a fixed depth, meaning we can't apply more than a certain number of gates. It's going to be of a fixed like geometric locality, so we can imagine the qubits being in a grid. In this case, they're in a two-dimensional grid, and they're stacked on top of each other. So this layer back here is the first layer of computation, the middle layer is the second, and the third. So this is depth 3. And yeah, we're going to denote it with this thing here, but Q and C0, for those familiar in the classical or quantum setting, is just local gates that are applied for constant depth, and the G just stands for geometric. And how we model our adversary, which is, I believe, novel to this work, is we're going to model the adversary as being an exponential time classical computer, or anything, any classical computer that can do whatever. And they're going to have access to a single one of these geometric quantum circuits that they can choose. And the reason we do this is because we have this auxiliary quantum state that we're given, right? I don't know if it's not here. We're given an auxiliary quantum state by Alice, this rho, and we would like to only have the restriction that Bob can only apply this G and C0 circuit to rho. But we don't want to restrict their other classical computation, their other quantum computation. So because there's an exponential classical power, they can simulate any other quantum computation. So I don't know, I think it's pretty neat. But basically, this gets rid of a lot of the annoying parts of dealing with auxiliary quantum states. Yeah. So the reason we chose this model of computation is because they have some nice properties, and they've been considered in the literature before. And really, we can start talking about what are called light cones. And light cones come up a lot in complexity theory for quantum circuits. And they're just a question of independence within the quantum circuit. So imagine we have a two-dimensional grid of qubits. These black dots are all qubits. And then the yellow spots, or the yellow parts within these qubits, are not going to be touching each other in the circuit, meaning that if we look at the output of the circuit and we project the light cone backwards, they're all going to be independent. And this is going to be key for our proof. And then the blue parts we can't really say too much about. So these yellow parts we're going to label as like Cu for cube, and indexed by I. And these outer parts have this little tilde upon them, and also indexed by I. So this is an example of our grid. So yeah, so now we're going to take what we have here and go towards a proof. Okay, so we have our Q and C0 circuit, and we're going to want to reorganize our measurements in terms of light cones. So if we think about what Bob can do, Bob can do any sort of measurement on their input qubits as long as it's a certain depth. But because this quantum circuit that Bob chooses is kind of fixed, we can reorganize the order in which measurements are done. And what this means is that we can kind of think about, first, we're going to give Bob all the information in the blue qubits for the purposes of the proof. So the adversary Bob is stronger than in the real world and has a lot of extra information. And so that's going to be a part of the classical computation. Then we're going to do a sort of progress bound. We're going to talk about Bob's going to be able to measure one of these yellow cubes at a time. And we're going to bound how much Bob can learn for each of these yellow cubes. And you use that to bound the amount that Bob can learn about the next yellow cube. So again, first we're going to have Bob measure this inner yellow cube, and then the second cube, and third cube, fourth cube. And we're going to use the bound on what Bob learned from the previous cubes to bound what he learns about the next cubes. And we can do this because the circuit's non-adaptive. Okay. So what I just said, we're going to give away the information for the non-independent parts, the blue parts. And then we're going to want to show at the end that there's a good amount of entropy left in either one of these code words, C0 or C1. And that's going to be our proxy. In the paper, you get the actual full proof of how you get to full one-time memories. But really, we're going to just want to show that at the end of the computation, there's going to be a high amount of entropy in one of these code words, meaning that it looks pretty random. And Shannon entropy, which you guys might be familiar with, is not enough here. So we're going to have to use a different notion. Min entropy, which you might also be familiar with, is too strong and is too lossy in the proof. So we're going to use something in between that we're going to introduce right now. Okay. But before that, any questions? Okay. So entropy is a very important concept in information theory, cryptography. It relates to coding in some ways. And within cryptographic contexts, min entropy is often used. But min entropy is a very, it's hard to work with in these type of protocols. So instead, we can use what's called random entropy of order 2, or termed collision entropy in classical literature, which is just the expectation of the probability of a random variable, of probability of x. And what that means is that if the collision entropy is pretty high, we should expect our event, like what x actually is, to look pretty random, because it's unlikely to get it again. It really helps bound the probability of collision, of seeing things twice. And there's a conditional variance where it's just going to be expectation of the probability of x conditioned on y. But importantly, we have this information quantity, which is similar to what you have in classical Shannon theory as well, where you can define how much the revealing of the random variable y tells us about x. So how random does x look after getting y? And we're going to be bounding that throughout this paper. And why is collision entropy useful? Just a quick recap. It's because it has this nice Markov chain inequality thing where we can upper bound the probability of we can upper bound the probability of our output not looking random by some small exponential. And that's going to be pretty important. It has other useful properties that we're not getting into here, but there's some code involved in this work that uses these properties too. So one of the new things we introduced in this work is these three quantities that have to do with random access codes and entropy, collision entropy in general, that we're going to use to get our progress bounds. And there's three things. There's the greater, this I greater than sign, is the maximum we can learn about one of the bits, either B0 or B1. This I tilde is the maximum we can learn about one of the bits given the other bit. So we know the other bit, how much we can learn about one of the bits. And recall that we have one quantum state, it's 1 qubit, and it's going to pack 2 bits of information in, B0 and B1. And this I total is how much can we learn about both of them from the same measurement. And importantly, these quantities are defined over uniformly random and independent B0 and B1. So the distribution over B0 and B1 are independent. There's a whole bunch of code for this. It's kind of brute force, a bunch of tricks to get these upper bounds. But what it's saying is you can't learn that much more about both bits at once than you can learn about a single bit, right? So we can learn 0.59 about a single bit, but about both bits at once, we can only learn 0.65. And that's going to be our main technique. Okay, so now we're going to do the proof outline. I think I'm really good on time, so if anybody has any questions, ask away. Yeah, so it's a space of POVMs for a single qubit. So it's you can, because of these convexity properties, you only need to search over the extremal POVMs, 4 at a time, and then and then some other tricks to not actually search over all the POVMs, but yeah. Cool. Okay, so now we're going to do our actual proof and how we go about it. And our key technical tool is the leftover hash lemma, which for those familiar with cryptography is this really beautiful thing, which says that if we have a two universal hash function, we can use it to extract out something that looks like true uniform randomness. So a two universal hash function is a compressing function which with the probability over the hash function itself. So this is like ill-defined, but don't worry about it because there's a family of hash functions and then the probability over the hash function itself. The probability of two distinct outputs mapping to the same thing is very small. And it's nice because if our collision entropy is sufficiently high on some string, and we put it into this two universal hash function, the leftover hash lemma says that the output is indistinguishable from uniform, meaning that statistically it looks very close to just completely random. And also, for the next slide that we're going to get to, random linear codes are nice because they saturate the Shannon bounds, which we need, but they decode in exponential time, which is bad. But importantly, the generator matrix of a random linear code G means a random matrix, like that's how it's defined. And the fact that G is a random matrix is very useful because I guess the next slide. So, so remember, so our protocol is, this is like a recall of our protocol, but here now our code words are just the generator matrix times the row. I think, I forgot who, but someone yesterday said that column space multiplication for defining your code space is the best way to do things. I agree. It's much more intuitive. Anyways, we have, so again, we have like these n-cubed states, and we're going to measure them all independently to get our actual protocol. So the important thing about having the generator matrix be random is that if we take sub-rows of the generator matrix corresponding to these different yellow cubes, that's actually a two universal hash function. Right, so like if we have a random underlying message R, and we take R multiplied by G, the bits corresponding to the index by this inner cube are going to be indistinguishable from random if RA has a high amount of collision entropy. And this is pretty nice because then the qubits corresponding to those yellow cubes, we can start talking about them as being indistinguishable from random access code states. And we can use the bounds that we previously introduced. So again, if we can model our adversary, we can now see that we can kind of say that the qubits corresponding to this first yellow region, that's the laser pointer. If the first yellow region over here are indistinguishable from random. And same thing for the second and the third. And in this case, we're going to assume that the adversary learns more about the first code word, C0. So we want to say this about the second code word, C1. And really, not to get too much into it, but it's not too difficult. It's pretty nice because there's like 0.4 n bits of information to get all the parameters to work out in each code word, C0 and C1. But because we have this 0.65 upper bound on learning this 0.065 upper bound about how much you can learn from both bits, we can upper bound the fact that by the very end of all the measurements, there's going to be a high amount of min entropy or collision entropy in C1. And that's basically going to give us what we want, right? Like after Bob does all his measurements, C1 is going to look pretty random. And we can extract out more randomness from that. That's pretty nice. So just to conclude, we're going to have an early lunch. This work constructs information theoretic, so like we don't make any computational assumptions outside of the bound on the quantum circuit. So we construct one-time memories using error correcting codes and quantum random access codes. We get some new bounds on quantum random access codes, and we have like some progress measure that we developed. The big open questions are how do we get rid of some of the constraints? So having the circuit be fixed, the quantum circuit, is not great. You'd want the circuit to be adaptive, meaning that even though it's depth bounded, it can still, adversary can change the quantum circuit min measurements. And then we want to remove random linear codes. That makes your construction take like exponential time to actually run. That's not great. So yeah, this is the bibliography.
Any questions for our speaker?